section 2.1, which are some application questions. Essentially, what you're going to be given are formula, and they're going to be written in function notation. The variable here is t, as you can see. T is only going to be usable in the range 0 to 36 because in the context of the story, 36 minutes is the entire duration of it. Because what happens is you have a tank that has 70 gallons of water in it. It's full, and the water is draining out, and it's draining out so that after 36 minutes it's empty. And there's a guy called Torricelli who created this formula that would allow us to predict what volume would be left in this tank at any given minute t. And one of the questions that we have to do is to fill in this table, which is basically how much is left at 0, the beginning, how much is left at the end, and some snapshots in between. Now, we can certainly do these calculations one at a time, and in fact, I'm going to do a couple right at the start. So, the volume at time 0 is 70. 1 take away 0 divided by 36 squared. But that's basically 1 squared, and 70 times 1 is 70. And that makes perfect sense. Right at the beginning, before you drain any water out, there are 70 gallons. So, now according to the story, it's empty by 36 minutes. So, the volume, when it's 36 minutes have gone by, is 70. 1 take away the time divided by 36 squared. Well, that's 70 times, well, that's 1, so's that, 0. 0 squared gets you 0, and so, just as you'd expect. So, looks like this formula stands up to experience. You start with 70, and 36 minutes later, it's empty. Now, if I wanted to do 9, 18, and 27, couldn't I just go in here and plug in 9, plug in 18, plug in 27? Nothing wrong with that. I'm going to do it on the calculator because I'm careless. And if I do it on the calculator, I make fewer mistakes. So you go into y equals, and you type essentially the same equation with an x where a t used to go. So 70 brackets 1 take away x divided by 36. And for some weird reason, my keyboard is acting up on me. So let me try that again. Okay, quit. Let's go back in and hopefully it's sorted itself out. Okay, clear. Okay, so try that again. It's 70 times 1 take away, instead of t, I'll put x divided by 36. And I'm essentially just going to do a table of values. So that guy is good. And I'm going to go second table setup now. And I'm going to do a little bit different. Normally we would do a start value and a delta x, and that's what we would do if we were doing, you know, some other calculation. But in this case, I'm just going to go down here and make that ask. That's all you do. Make that guy ask and leave that one exactly as auto. So go to here and make that ask. Now, second table setup, right? Change that guy to ask, doesn't matter about the rest, so leave him alone. And the last thing you do is second, right at the end, table. And I'm going to put in my table, 0, and then 9, and then 18, and then 27, and then finally 36. Oops, put an extra 0 in there. You see how quick that was? And I know that each calculation is going to be correct, provided that my original function was correct. And I find that just more efficient. And I got all these numbers. Oh, two versions of it. So if you were going to this question here, you'd just be essentially typing in those values. So you would be doing 70 here. And do they ask for accuracy? Yes, 3 decimal places. So 39, let's check the second one. 39.375, yeah. $39.375, 17.5, 4.375, and last but not least, 0. Don't know what that answer is, rub it out. And let's check it out. And there you go. And this one we already did, which was what, 70, and this one we already did was 0. So pretty straightforward. You can do each one by hand if you want. It's not a big deal if you decide to go that way. I just find it more convenient not to do that. So there is only one last thing we need to calculate, and it's a thing called the net change. And the net change is basically the difference between the beginning and the end. So it would be value at 36 minutes, right? So the volume at 36. Subtract the volume at 0. So you notice it's end, take away, start, right? And this guy is 0, this guy is 70. And so the answer I would get is -70. So what that's telling me is that from the beginning, t equals 0, to the end, t equals 36 minutes, the volume has reduced, because it's negative, by 70 gallons. And just to verify that, I'll go in here and I'll hopefully change that to -70, which is what it should have been the first time. And submit my answer. Yeah, everybody's happy. So you'll be given a function, a formula that represents some kind of physical reality, like how much volume is left from a tank that's draining, or what the temperature is going to be after a certain number of minutes, or whatever it may be. And in each of these cases, you then will evaluate it at different points. Now, that's all well and good when the function looked just like the one we did. The next one is a version of question 2. So this one has a little bit of a kicker in the tail. According to the theory of relativity, the length of an object, L, is a function of its velocity. And the formula for how long something is, that may have started off at 20 meters. So imagine it's not moving at all, right? It's 20 meters. The length of that object becomes 20, the square root of 1, take away the velocity squared, divided by c squared. Now, what makes this a little bit different from question 1 is that c is actually a constant and it's the speed of light. And there's some ridiculously big number that we don't need to know, but they tell you it's about 300,000 kilometers a second. That is fast. But we do not really need to know that, because the velocities that they're going to give us in these questions are not going to be hard numbers like 200,000 kilometers an hour. What they're going to be instead is fractions of light. So, for instance, if I tell you that you're traveling at 0.6 c, we would say you're traveling at 0.6 the speed of light, which is kind of what astronomers would do. Rather than tell someone the numerical value, which is kind of weird and big and hard to understand, if I said you're going at half the speed of light or 0.6 the speed of light, do you see you get a better idea of what's going on here, right? It's just a different way of representing it. So let's find out what the length of something going at slightly more than half the speed of light. Its length, you can't really do this any other way except as a single calculation. It's 1 take away 0.6 c squared all over c squared. And it's 20. 1 take away 0.6 times 0.6 is 0.36 c squared over c squared. And something really cool happens. Do you notice that c, the speed of light, gets cancelled out and you're just left with a decimal? That cancels with that. And now you have 20 times, well, the square root of 0.64. And at this point, I'd probably go for my calculator and just type that in. And I have 20 times the square root of 0.64. And a rather weird thing happens. Oh, by the way, can you see my calculator right now? Because I've got it on top of my whiteboard. Or can you just see the whiteboard? Right, you just see the whiteboard. Fine. Now, that is kind of weird. And if you're into Einstein's theory of relativity and special theory of relativity, these things just are what they are. What that tells me is that if you were an object that was 20 meters long, and you go at 0.6 the speed of light, you will shrink to 16 meters. What do you think is going to happen if I go even faster? Let's suppose I decide to go 0.9 times the speed of light. Do you think I'm going to be even smaller, shrink in size? I wonder by how much. So it's 20, the square root of 1 take away 0.9 c, right, the velocity, squared over c squared. That's 20 square root of 1 take away 0.81 c squared, 20 square root of that guy, 20 square root of 0.19. And I will do that. Just tell you what I get. 20 times square root of 0.19. And I'm now down to roughly 8, what do they want, 2 decimal places? 2 decimal places. So 8.72 meters. If you go even faster, and then faster and faster, right? They don't ask this question, but I'm interested in it because I want to see what happens if you go the speed of light, not half the speed of light or 0.6 or even 0.9, but the speed of light. Let's find out what happens to this poor object. Agreed? Velocity, c squared, divided by c squared. Wow. So if people say, or you hear them say, you are not allowed to travel the speed of light, you might say, well, why aren't you not allowed to travel the speed of light? If you traveled, Alice, at the speed of light, won't you disappear from the universe? Your length will be zero. You will no longer exist. And the closer you get to the speed of light, won't you become like an atom in length? So we have a physical, this formula tells us some realities that at first sight seem really weird, that things that move very, very fast, fractions of the speed of light, shrink, and they shrink and shrink and shrink until they basically disappear. So I guess the only reason that light can travel the speed of light is because light doesn't have a length. It's not an object, right? It doesn't, you can't measure it, it's a wavelength. So I guess I've learned a little bit about physics. Now, each time you come across these questions, these formulas, they start getting uglier and uglier, and there's not really anything I can do to make them nice. So next one I'm going to show you. Are you looking at an eye staring back at you right now? Okay, let me get comfy with this fella. It's question 3. When brightness X of a light source is increased, the eye reacts by decreasing the radius R of the pupil. So you ever been at the doctor and they shine a light at you, and one of the things they're looking is to see that your pupils contract. Because if your pupils don't contract, that's a very good sign there's something really bad wrong with you, right? Because that is one of those reactions you have no control over, right? Your body will do it automatically. And they can actually use this weird looking formula up here to tell what the radius is, which would be the distance from the center of the eye to the end of your pupil, would be for any given brightness X. So, if I shone a very faint light, your pupil probably wouldn't move at all, right? But if I shone something that would, like, the beam of a headlight, it would hurt your eyes, but it would shrink a lot. So here it is, the ugly formula. And here are the 3 different brightness levels, right? 1, 10, and 100. Now, I don't know what units they use. There are certain things like, I think it's some weird name like candles, like 100 candles would be a unit of brightness. Right. So 1 candle of brightness, 10 candles of brightness, 100 candles of brightness. And we would make up a table just like this one. And I'm going to do now, I don't know if this is going to work directly, but I'll see. Can you now see my calculator, or will I have to go in and out again? Can you see it? Oh, great. Right, so I've got this formula over here. So I'm going to hit y equals. And I'm going to do a square root of, and as a fraction, so it's a good idea to do a bracket and do 13 plus 7 times x to the power of 0.4. Then get out of there and close the bracket. So that basically represents the top fraction, the numerator. Then I'll do divide, and I'll start another bracket, and I'll go 1 plus 4 times x again to the power of 0.4, move outside and close the brackets. That looks good. Now I want to do this table of values, right? Different strengths of X to see what would happen. I'm going to make a prediction here. As this gets brighter, shouldn't that radius get smaller? Right. Now, let's see if I've got the thing. Now, I've already set up the table. Oh, my calculator reset, right? So I'm going to go down then and set it up with that guy saying ask. Right? That's all you need to do. And then you go second table. Okay, here goes. 1 candle of light, 2 millimeters. Okay, if you plug in something that's 10, if you plug in 100 units of light, if you plug in 800 units of light, something that's even brighter, 900, if you put in 1,000, right. Makes sense? Now, I'm sure your doctor would never use anything that was that bright that it would, you know, burn or hurt your eye. But just for example's sake, because I'm curious now, I wonder what would happen if you used not 1,000, but 10,000. Do you see that the difference is quite minute? So I guess what that tells me is, do you know that your pupils can contract, but they can only get so small, right? That's as good as it's going to be. And that number looks to me to be around about 1.3 and a bit, right? So for a normal person's eyes, they can shine it. And if it gets about 1.3, they know that's it. It's as good as it's going to get. And they finish with a net change. And in this case, you have to be careful. It's 10 to 1,000. Right? So you would put in the brightness at 1,000, whatever that happened to be. Take away the R value when the brightness was, what, 10. And round that on, so that particular answer to 2 decimal places, and you are good to go. I mean, it's a pretty ugly formula, but once you know it's just something that the calculator can handle for you, isn't it a lot easier to just find a table of values and see a pattern, which in this case was pretty obviously a decreasing pattern. Lost the guy, there we go. Remember, decreasing pattern. Now, the next one I'm not going to do, but here is the formula that you're going to use. And what this formula does is it tells you the velocity of your blood going through an artery, right? A big, thick vein, an artery, right? Something like bumping into the heart. And the blood does not go at the same speed. You might have thought it was like a constant, no matter where on the edges they are. But actually, if you measure the distance from the center of the artery to wherever it is, and you call this distance little r, then your velocity is this. And you can see in the picture here that the velocity is strongest in the center and it's weaker on the outsides. Well, so as blood goes through your arteries and your veins, for that matter, the velocity at which the blood is pumping is not a constant number. It's faster in the middle and it's weaker on the outside. And this formula here essentially tells you what that value should be. And technically speaking, if you calculated the answer at the edges, it would be the slowest. And if you calculated it right at r equals 0, it would be the fastest. And as far as I know, and I'm not a medical person, but arteries, and especially when you get older, there's things like plaque that stick to the inside of your arteries and they cause blockages and, you know, bad things to happen. And one of the reasons these things can happen is that at the edges of your artery, the blood is not flowing anywhere near as fast as in the center. And can you imagine like it's a river, and at the edges of the river, when the river's not traveling very fast, isn't it possible for things to just stick and slowly join the edges of your artery? And that is bad news for anyone. And we try to avoid that. But this tells me the mechanics of why that is happening. And you go in and you fill your table and you come up with your answer. This one is the surface of a sphere. There's nothing weird about that one. Oh, let's do 6. It's kind of interesting. The distance to the horizon is given by 2rh plus h squared. And r is a fixed number. It's the radius of the Earth, which is 3,960 miles. So if you didn't know that, you now do. And h is the height at which you are measuring to the horizon. So let me jump over and do a really, really poor picture because I'm not an artist. Right. You can imagine that you have a tower, a lighthouse, whatever, and you're at the top and you're looking as far as you can see. But because of the Earth's curvature, there's a point, isn't there, where that's as far as you can see. Right? If you've ever been at sea and you look out to the Pacific, right, you don't get to see Japan. Doesn't the curvature of the Earth stop you from seeing that, right? We call that the horizon, right? So if you were looking, how far away would you be able to see a ship in the olden days, right? Well, if you had a really tall tower, wouldn't you be able to travel and see further into the horizon? And this formula here tells you what it is. Now, since they told me the radius, I'm going to rewrite the formula as the square root of 2RH, which is twice that guy. Okay, twice 3690, so it's 0,297. So it's now that guy plus h squared. So there's our formula with h's. And we are going to find the distance that you can see when the height is 0.3 of a mile, right? So 0.3 of a mile, if you want to know what that looks like in feet, let's do that quick calculation. 0.3 of a mile. It's 0.3 times 5,280. Wow. So if you were in a tower that is approximately 1,548 feet tall, right? That's a pretty tall tower, right? If you were in the top of that with a pair of binoculars and you were looking at the horizon, how far away would you be able to see? So let's see what the answer looks like. It's the square root of 7,920 times 0.3 plus 0.3 squared. And I'm just going to do this on the calculator at the side. Hopefully I don't hit anything wrong. So it's going to be the square root of 7,920 multiplied by 0.3. And then I'm going to add to that 0.3 squared. And the answer I come up with is that you would be able to see only 48.7, how many decimal places do they want? One decimal place, so 48.7 miles. Now, in the days before radar and radios and all sorts of gizmos like that, can you see that if the horizon at the top of a mast, which was 1,584 feet, so that would be a really tall sailing ship, you could only see 48.7 miles into the distance. So can you imagine the poor guys in sailing ships looking for land? if that land was 50 miles away, you wouldn't even see it, would you? Even at the top of the mast, you wouldn't notice it because it's beyond your horizon. So those people were kind of brave, because if you didn't really know, or you made a bad job of navigation, you wouldn't really know when you were near the end. Okay, any questions with what I've done so far, right? You got a formula, you plug it in, you get an answer, and then you can make interpretations. I would make a prediction here. If the height h was bigger than 0.3, I'd be able to see further. That would be my prediction. So next fella is going to be a version of 7. And we're going to look at a piecewise function, not to sketch it, but to evaluate it. And piecewise functions are basically formula where the value or the formula that you use depends on the value of x. So here is a rather messy piecewise function. And in a certain country, income tax, how much you pay, is assessed according to the following formula. 0 income tax if you make between 0 and $10,000. And if you make between $10,000 up to and including $20,000, then the amount of tax you pay will be 0.04 of x. And if you make more than $20,000, this is the formula. This is the formula for how much tax you would pay. So let's pick some random people. John doesn't have a great job. He only works part-time. He makes $6,000 a year. What will his tax be? Well, what you do is you decide which formula works for him. Since he's only 6,000, that's your x, and it's in this range here, his answer is simply just 0. Now, let's say he's got a brother, and his brother, he makes 15,000. Well, if you make 15,000, do you see that you now qualify in the middle category, right? X is between 10 and 20,000. So he's going to be 0.04 times whatever x is. I'll do a quick calculation to see what that comes to. And that's essentially 4%. So 4% at 15,000. And he pays 600. So he's got a tax bill of 600. And let's say someone else in the family makes $80,000 a year. Well, 80,000 belongs under the third category. So his tax or her tax is going to be 800 plus 0.13 times 80,000. And again, I'm just going to hit the buttons in calculator and come up with the result. 800 plus 0.13 times 80,000. And this poor person is going to pay $11,200 in tax. So do you see how the piecewise function is really 3 formulas? Each formula is for a certain circumstance, and the circumstance depends on what the value of x is. Between 0 and 10, use the 1, 10 to 20 in the middle, anything over 20, you use the bottom. Are we cool with that question now? Piecewise function. Once you get the hang of them, they're not really any different than anything else. What do you do here? No, it's too straightforward. Can't really avoid this question, or at least pretend it's a different one. So let's just look at it. Quite different from anything else in this section. It is a graph where the x-axis, the horizontal axis, represents time, and the vertical axis represents the temperature. So capital T is temperature, little t is time. And they have a story at the top. And one of these four graphs is going to be a good representation of what you would get. Right, so let's see. You place a frozen pie in an oven and you bake it for an hour. You then take it out and you let it cool, I guess on the kitchen table, until it reaches room temperature, and then you eat it, right? So it starts off frozen. It goes inside the oven. I'm assuming you heat it up, right? Cook it, make sure it's nice, no germs in it, whatever. Bring it out piping hot, leave it on the table, wait till it gets to cool room temperature so it's safe to eat, and then eat it. Only one of those four pictures represents the temperature that you would notice if you recorded it throughout the journey that we just described. So here's your question, which one is it? Which one of those represents that story about the apple pie? I see three, and I'm assuming you mean that one, right? And I agree with you. Do you want to share why you picked that one? Because it's right.
Me?
Yes, Elise.
Because it went in the oven.
Okay, so it started frozen and it went in the oven. So you said it went up, right?
And then it had to bake at that temperature.
Okay.
And then you take it out and then it cools, but it doesn't go frozen again.
It kind of levels off at room temperature.
Yeah.
Great. Is that the kind of thing you sometimes see in physics classes where they tell you about things moving and journeys and stuff? Is that a skill that you've used in other contexts, or is this literally the first time you've seen one of these?
I think in like chemistry.
Okay, so sometimes they talk about chemical reactions through time or temperature through time. Right. So that was it. There's four guys. And to finish with, I'll write this formula down and we'll kind of work with it. So it's 2000. It's a 7x. It's a 0.01x squared. And it's an even smaller 0.000. That 1, 2, 3, 3 zeros. 9x cubed. Okay. So for our last and final question for today, what we're looking at is basically just another formula story. And this is the formula here. And this is C, the cost in dollars of producing X yards of a particular fabric. And so I want you to think of this as a factory production, not somebody just making one at home or something. So we're talking what it might cost in different circumstances. So you could be asked to find C of 10, or you could be asked to find C of 3, and you could also be asked to find C of 0. Now, if a factory is producing this material, right, and you wanted to produce it in, let's start with the weird one, 0. That's the easiest one to calculate, because isn't the answer 2,000, meaning $2,000. And you might say, but you didn't even produce any of the fabric, yet it's still costing you 2,000. And we have a name for that. It's called the fixed cost. So if you're into accounting and that kind of thing, that's an important fact to know. What is the fixed cost? See, if you've got a factory, and it really doesn't matter how much or how little of something you produce, there are certain things that are just going to cost you money. Let's suppose you don't own the factory. Aren't you going to spend $2,000 a month or $2,000 a year renting it? That's a fixed cost. Doesn't matter how much you make or don't make, that's fixed. You might have to pay property taxes, and maybe you've got people working for you. Even if they don't make anything, you still have to pay their wages. All those things are fixed costs. Now, let's find out how much that guy costs, and let's find out how much that guy costs, and see what our final result looks like. Okay, I'm just going to go to the calculator. It'll take me a few minutes, so you have to bear with me. Actually, while I'm doing this, because you're just going to sit and listen to me for a few minutes, why don't you put your last name in for attendance? And while I get this thing typed into the calculator. So it's 2000, add 7x, add 0.01x, add 0.12309. I have to go here and I've got something. I fixed it. Good. Add 0.0009x cubed. Okay, so you all have typed in your attendance. Right. So let's zoom over and look at this guy. There's my function. And I'm going to go to second table setup. It's already good to go. I should be able to go to table then. Table. Come on, hit the button. There we go. Now, I don't know why it took so long. Now, I'm going to rub out this data. That's from the previous question by hitting delete. Okay, now, if you put in 0, there's that $2,000. If you produce 10, it's going to cost you that. If you produce 100, it's going to cost you that. And if you produce 1,000, it's going to cost you that. I'm a little bit worried about the 1,000 one now that I've plugged it in. Would you agree that 919,000 is almost 1 million and really, really big compared to all the other numbers, right? I mean, if I only produced 100, it's only going to cost me $3,700, right? So the only thing I can think of is that there's a kind of capacity that this factory can produce, right? You know, if you try to produce any more, you'd have to go buy a new factory, buy new machines, hire 2,000 workers, pay everybody overtime, right? It would just be extortionately expensive. So that last number is telling me that this factory should probably not try and produce 1,000 yards of the stuff, because they'd end up, it would cost them so much money they'd go bankrupt. I wonder if they could do 200. Yeah, 200's expensive, but they could probably handle 200, right? But they definitely couldn't handle 1,000. And this is a perfect time for us to finish. So bye-bye for now, and I will hang about for any questions that you may have. Otherwise, same place, same time tomorrow, we'll be online.